Hello, everyone, and welcome to today's graph reading group.
Well, we're joined by Nicholas Gao, who will tell us how he uses GNNs to solve the Schrödinger equation. So let's go.
Okay, then I would like to thank Dominique and Hannes very much for inviting me to give here my brief presentation of our ICLEAR paper of 2022, Ab-Initio potential energy surfaces by pairing GNNs with new wave functions. So let's get to the basics, what we're trying to solve here actually. This could be phrased as like molecular modeling. So you can imagine you have a molecule, which is like atoms in 3D space. So you have some positions, and then you have some atomic charges associated with them, and then you want to predict some properties of that. We will here only focus on the energy of the molecule, because that's the driving force in like chemistry. Like everything is searching for its lowest energy state, so knowing the energy is quite important. And if you can solve the problem, then you can like apply it in like binding energy predictions, molecular dynamics simulations, or if you want to replay reactions, which then in turn lead you to new drugs, catalysts, materials. But then the fundamental question here is obviously, how do we obtain the energy of a molecule in the first place? And this is where the Schrödinger equation, which we just talked about, comes in. So let me see, wait, I can get a pointer here. Okay, I hope you can see it. So here above, you see the Schrödinger equation, where we have like this H here is the Hamiltonian, which is an operator. So given a function, it returns a function. And then we have like a psi, which is it's called a wave function, which takes like n inputs, and these n inputs are electron positions as an input. So this wave function defines over a function which takes like n times 3 as an input and returns some amplitude for that. You could think of it kind of like a probability distribution, but actually its square is a probability distribution. And then on the right side of the equation, we see like E, which is an eigenvalue of our Hamiltonian, and the wave function again. So if you know basically in the algebra, you have seen these like metrics, eigenvalues, eigenvectors. So this is also an eigenequation, but now in function space instead of some finite dimensional vector space. So we're searching for the eigenvalue E here. So the eigenvalue is the lowest eigenvalue we're searching for. And we do this by updating our wave function and then applying this operator over and over again. And okay, there might be scenarios, yes?
Yeah, so like what's now the physical similarity or the physical parallel to these equations, right? We have our wave equation, it takes some atom and some electron locations, and then it gives us a number. And now what is the physical interpretation of the Hamiltonian and the E? And you said that this number that it gives us, that is can be like like an unnormalized probability.
Yeah, yes, exactly. What we can think of, like the wave function itself, is in quantum physics, like you use waves to describe everything, and these wave functions are defined as like being the square root of a probability distribution. So if you now take the squared probability, psi, then we can model the probability distribution of the electrons, and with that you can model where they will be in space and so on and so forth, and which orbitals they have. The Hamiltonian operator is just defines the system in itself. So this is where the nuclear positions will be in. I haven't written it out here. It essentially consists of some kinetic energy term and some potential energy term. And yeah, and the takeaway generally is that this defines the system, and you can also replace as a Hamiltonian by other Hamiltonians depending on other applications you want to focus on. But we only care about molecules, like simple molecules here.
Okay.
In vacuum. Yeah. While this equation looks easy enough, unfortunately, we have no analytical solutions for these Schrödinger equations in general if you have more than one electron. And only one electron is not that interesting, because then you only have a hydrogen atom or something like that, but you're interested in more complicated systems, molecules, proteins, and they are way, way larger. So what this leads us to is approximate solutions. And there you always have to find some trade-off between like computational costs and accuracy, where generally, if you want to be more accurate, you always must pay more compute. And this is more like a strict relationship. For instance, Hartree-Fock theory here which is not very accurate, is like n to the 4. Then we have coupled cluster theory, which is n to the 7. And if we want to be exact, we have to do like full configuration interaction, and then it scales factorially with the number of basis functions you choose, which is generally like, you can think of being larger than the number of electrons. So this is super expensive at the top here, where you have to do like factorially many calculations. This is infeasible if you have more than 4 electrons. Fortunately for us, in practice, there exists one outlier, which is called density function theory, which you will heard probably, like if you work in the field of molecules, will have heard most about like density DFT, because it's what people generally apply. It scales n to the 3, but is way more accurate than Hartree-Fock and can even reach like, if you're lucky, like coupled cluster accuracy for certain molecules. So this is super high accuracy compared to its computational cost. But what we are going to focus on is what we call deep quantum Monte-Carlo. Scales more like n to the 4, so it's similar theoretically scaling than Hartree-Fock, but way more expensive due to large prefactors. But has way higher accuracy again than DFT, and is comparable to coupled cluster or even like full configuration interactions on smaller systems. So yes, so we are now focusing on these Monte Carlo methods, and the motivation for this is simply that they're relatively cheap, but give high accuracy. So how does variational Monte Carlo look like? Which is just one kind of quantum Monte Carlo. You generally pick some function psi. So the wave function we had before in the Schrödinger equation, you now pick some function which has some parameters. And then the idea is that we optimize these parameters such that we will eventually end up at our ground state, at the lowest eigenvalue. And we can do this numerically by, as I said, the square of the wave function is some probability distribution. So we can sample this probability distribution with some Monte Carlo process. And then we use our samples to numerically approximate this integral here, where we try to estimate the energy. So this now looks kind of wanky and not exactly like the equation we see in the first slide, but with very simple math, you can show that you can reformulate the first equation to this one, and then you can get an energy of the estimate and an estimate of the energy. And with that energy value, you can compute some gradients, and then you just do a gradient step, and then you have your normal optimization loop. So while this is not a supervised training, as you've seen like in other like neural networks for molecules, where you first do DFT calculations and then train a network to reproduce the DFT calculations, we actually perform these whole calculations on the network itself. So this could be think of like the most common comparison could be reinforcement learning, when an agent acts and then it gets feedback and then you improve upon yourself. This is more like self-consistent learning, where you get your electron positions, you evaluate the energy, you optimize the energy, get new electron positions, and so on and so forth. Yeah, and the beauty about this simple framework is that we can use pretty much any arbitrary function for psi, which has very few requirements. So the idea is then just let us use new networks for this. However, like as I said, it has requirements, and the first one, it must be anti-symmetric if you exchange to electrons. This is just some physical property related to the Pauli exclusion principle. So this is just it has to be there, it must be there, otherwise it doesn't work. Because electrons are fermions, and the fermions have this property, which is, again, this comes from quantum physics or quantum mechanics, and this is just a given thing. And this anti-symmetry here means that if we have a function of n electrons, and if we swap 2 electrons, the sign of the function must flip. And the easiest way we can incorporate this is by just using a new network, which outputs us some embeddings, and then we concatenate these embeddings to a matrix, and then we take the determinant of the matrix. And here we are using the fact that if you take the determinant of a matrix and you swap 2 columns or 2 rows, then the sign of the determinant flips. Yeah.
Can we?
And one key problem, yes?
Yeah, that's a nice solution to that. But can we maybe go back to the problem setting a little bit to make clear what we're trying to do here, right? We want to find our wave function, and the wave function is the thing that gives us the probability of a certain state existing. But now in your Schrödinger equation, if you maybe go to that, you always have this h, which we get from the outside, right? Which is just something that we're given, but the e we actually also don't know, right? We want to yeah, and now in your variational Monte-Carlo thingy, on your variational Monte-Carlo slide, there, how do we then always find the e?
Right. So this energy here. Okay. In this equation here, we're referring to the eigenstates. So here, given like some psi, which is some eigenfunction, and we apply the Hamiltonian operator, we get this eigenvalue, which is like normal, like in linear algebra. So this is just linear algebra. But if you go here, this energy value E, you can if our wave function is now not the eigenstate itself, but some linear combination of other eigenstates, right? Similarly, like if you had like a matrix and then you have a vector which is not one of the eigenvectors, it will be some linear combination of the eigenvectors. And then you multiply it with the matrix, and then you still get this prefactor, which will be a linear combination of the eigenvalues times the original vector, right?
And yeah, and here, what do you mean with the expectation over the probability?
Right. So the notation on the previous slide is not super, like what physicists like to do is that they always use this bracket notation, which essentially boils down to being inner products in some vector space. But here we can, I will not use the whiteboard. Let me see. I can draw here also, right?
Yeah.
Our PowerPoint is not working. Okay, no. Okay, I've got it. Okay, let's hope I can draw. So usually you write it as like, sorry for my bad hard drawing. I have to use the trackpad.
No, I think
so you have your wave function here, and then you have this is an eigenequation, your energy value here, and then you have again your wave function here, and again here's these notation with these weird brackets. This is like physics notation. This essentially just means this is some element of some vector space. You can think about that, right?
Yes.
So again, this is like a function space. Now we can multiply the whole thing by the transpose of that. So then we get like transpose psi, or like Brad psi, how it's like then called, and then our operator. And because let's now assume that our function is normalized, just because it's easier, it also works out if it's not normalized, but then it gets on the right side to 0, because if it's normalized, then the inner product of the same of a vector element will be 1. So this cancels out, and we have it on the left side. And then what this thing on the left side means is essentially we evaluate an integral over the function arguments. So the inner product between two functions is like the integral over their space. So this would be some x, and then you have like psi, and then h, and so on. This is very bad at drawing, but so essentially this bracket here notation means that this is some integral, which is the same as the expected value, right? You can also phrase an integral as an expectation value, and then you do some tricks to get to the sampling procedure here. I can derive that, but then I can share my screen with an iPad, and then I can derive it for you if you want to.
Yeah, but so essentially what you're doing is you're taking the to finally really compute your E, is that you take the integral over your psi squared theta of all of the positions that you sampled, and like a single set of positions, and then you have this psi h psi term there, and yeah, that whole integral is something you need to compute.
Exactly. This integral is what we have to compute at every step. And we approximate it numerically with Monte-Carlo. So this is why it's called variation Monte-Carlo, because we approximate all of our integrals with just Monte-Carlo estimates.
Yeah, okay.
Nicholas,
so you have two sampling steps, right? Yeah.
No, we have one sampling. We sample here our electron positions, and then we use these electron positions as samples from to approximate this integral here. Like we use these electrons which we sample here to approximate this integral.
Okay.
Nicholas, just to check. So the goal here is to finish up with a wave function. So what we're trying to find is a wave function that defines our like Boltzmann distribution, or
it's not necessarily Boltzmann distribution, but we're trying to find the lowest eigenstate. So the Hamiltonian operator has infinitely many eigenfunctions, and we're just trying to find the eigenfunction associated with the lowest eigenvalue. And because this is we have the variation principle, you will, like, this is similar to power iteration on finding like the largest eigenvalue of a matrix.
What does this wave function represent physically?
The square, like, it has no indirect physical representation. This is because it's an abstract thing, more or less. This is also why the sign of the wave function doesn't matter. But its square is the probability of finding each of the n electrons at the specified locations, right? Because it takes n positions. Okay. And then the square of that wave function is the probability of finding, like, the density of finding each of these electrons at their respective positions simultaneously.
Thanks.
Yeah, basically the wave function is what you're trying to solve in the Schrödinger equation, which states basically that electrons behave like a wave. Yeah.
Like if you see here density function theory, that works on the electron density, which is you get if you take the square of the wave function and integrate out all but one electron position. And this is then the theory of the whole density function theory. I will not go into any details of this because it's not really related to this work. But these are different ways of how you can represent essentially the electron behavior on molecules.
Okay, yeah. So we want to solve a Schrödinger equation, which means finding the parameters, or which means finding the wave function. And one way to do that is to have an initial wave function and then optimize its parameters by sampling according to the probability that the wave function gives us, sampling atom locations according to that probability, and then computing the energy that's given by the energy that our current wave function gives us for the locations that we sampled, and then doing a gradient step to minimize that energy. And then we eventually end up with the wave function that corresponds to the lowest energy eigenvalue. Yeah.
Exactly. Yeah. That summarizes it.
All right. But now this is slow.
Yeah, let's first talk, like, we want to use now new networks as our wave functions, because they're flexible. Like, we have this universal approximation, we can approximate arbitrary functions, which is great, so we want to use them. So we incorporate, as I said, like the symmetry by using some determinant and some permutation equivariant network here. So you can think of it like being a GNN. If we swap two electrons, and also they're embedding, like, in the output, the corresponding vector swap, and then we take the determinant, and then we get this anti-symmetry. The second property, because its square must define a probability distribution, that its integral must be finite. And if you now imagine like this being some wave function, then obviously its integral will not be finite. But we can quickly enforce this by using, like, for example, if these would be our electron positions, we're just having some exponentially decaying envelope. And at that point, and then if you multiply these two, you get a function which will have a finite integral. So with these two tricks, we can get a new network, which then works great in our framework, which we just described.
So trick number 2 is that for every atom location, no, for every you just take the final output of what we have in trick number 1, and then you multiply it with some value or with some function that only takes on high values around the electron locations, and is very, very small everywhere else. And that way our integral is always finite.
Exactly. Like, we're not applying it to the very end. We're applying actually it's a state here, but yes. We're just multiplying this, and then our determinant will, and then our function will vanish at infinity. Okay. So these are previous results from Frank Noé, Jan Hermann, and David Fau, and so on, which have been shown to be like very accurate, but also quite expensive, because like every time you want to get an energy value for one geometry, so one specific 3D constellation of a molecule, it takes a few 100,000 iteration steps. And like in terms of compute time, these are for you, like for larger systems, a few 100 hours. So this is not ideal, right? And we want to do this quicker if we get to larger system, to bigger surfaces. Specifically, why we want to like evaluate many energies is generally the concept of the potential energy surface, where you, which is like a hypersurface over all geometries. So it assigns each individual geometry an energy value. And for example, if you think about like in dimer, so two atoms, they only have a distance. Like everything else doesn't matter. There's only a distance between these two, and you can assign to each distance an energy value. And this defines like fundamental behavior of atoms. For example, like here, these hydrogen atoms, they have some optimal distance where there's the lowest energy. And if they would be like further apart on the right, for example, they would be separated, and the energy just converges to the sum of two hydrogen atoms in isolation. And if they get too close to each other, they'll pulse each other because they're positively charged. So this energy surface defines like the behavior of atoms, when they react, when they form bonds and stuff like that. So we are definitely interested in modeling these things. Unfortunately, with the method I've just shown you, we can only evaluate a single data point at a time, and that's already expensive. So doing it for many is just takes time. So traditionally, what people do is like you have your energy surface, then you subsample a few data points, you collect them in some database, and then you train a new network or some other polynomial function or whatever you want to use on top of that, and then you can have an analytical solution for your energy surface. But the expensive bit here is that you have these many data points here which you have to evaluate, and each of them is quite expensive. And then if you want to have an accurate model in the end, you must sample many data points. So this is the expensive bit of the whole pipeline. But now first, a quick detour on which model one could use. Why I said you could use like MLPs or like polynomials. Nowadays, it has been found that graph neural networks perform super good at this task. So we'll talk a bit about these supervised learned graph neural networks, where you take these data sets and try to infer the energy surface. And the idea is generally that you formulate like learning the energy surface as a regression problem. So you have these individual data points, and you just fit your GNN to match them. And the GNN works by exploiting the graph structure of the molecule. So you have your point cloud, and then you take nearest neighbors as edges, and then you communicate messages about the geometry. And this way, each nuclei encodes its local geometry in its hidden state. And then it has been shown that these are very accurate reproductions of the data set you handed to. And also the inference time is super fast, because you just need a single neural network forward pass, no complicated optimization, and no integrals you have to solve, and so on. Unfortunately, but then only works.
In this scenario, right, our training data are we have a single molecule and many possible conformations of that molecule, and we know the energies of all of those conformations, and then we train our network to take a 3D configuration and tell us the energy, like the single number.
Exactly. Okay, this is a supervised training setting here, which should you.
Then we can also hopefully do that for many molecules, and then generalize to new molecules.
This is not discussed here. This is just for the simple case that you have one molecule and you want to know the energy surface of that set of atoms.
And if you say that people do that a lot and they're yeah, this is something that actually graph neural networks work pretty well, then what sort of training data do we have from the potential energy?
Exactly. Like typically, like if you see like data sets online, they will use like DFT calculations. For example, like QM9 is with DFT. There's MD17 which is DFT.
Do we have 10 samples or 1,000 or 1,000,000?
It always depends on how big your energy surface is. Like people in like these fields rarely look at 2 atoms, but like more bigger molecules which have higher degrees of freedom. Because like in this simple case where you just have like 1 energy surface, you can sample 16 data points that could fit it quite well. But if you have like a 10-dimensional energy surface, then the curse of dimensionality will get you to sample many data points. For example, like MD17 has a few 20, I think 60,000 long trajectories of MD simulations, and then there's like OE62, which is also a big data set in QM9. And all these data sets take a different task, so they're all way beyond what we are doing here, and like in terms of scale, because this is only like we're talking about very much about very small molecules here. And these data sets are only concerned about big molecules of DFT and so on, which is not really the same scope as this one.
Okay, and then is how people, sorry, I have some COVID. Then is the way that people actually use this, these energy functions that you trained, mostly that they then go ahead and take like some gradient of their energy function and get some forces with which they do molecular dynamics, or are there also other uses?
Well, there are different use cases you can do in general with like these learned potential functions. Most commonly used for molecular dynamics simulations, but in general, like if you're given any arbitrary molecule, you first want to find its equilibrium structure. So this would be the first process. Like given some molecule, you want to find its lowest energy structure or conformers.
But I mean, if you have a lot of experimental data with which you train your model, then you probably already know that, right?
Yes, like then what people traditionally do, like to get the they first use some very rough empirical methods to get the equilibrium structures. So they first do rough calculations, and then they do higher accuracy calculations after they found interesting states. So usually people use their traditional force fields, which are just fitted to some other methods. And then you select the interesting data points, for example, extrema in your energy surface, and then you evaluate these with DFT. For larger things, DFT. For small things, you can use coupled cluster theory.
Yeah, okay. Thanks for all the detailed answers to the many questions.
Yeah, no worries. So this is essentially the last slide before I get to actually what we have done now. So this is again recap. So you can use these GNNs to learn these energy surfaces, which work great. And then our idea is simply, why don't we combine these two things and and have adaptive wave functions, such that we can model wave functions of many systems simultaneously and avoid doing many trainings, but just train once for multiple things. So as I just said, like the idea is that like we have adaptive wave functions. We want to, given a geometry, return a wave function which solves the Schrödinger equation for that geometry. And the simple motivation for this is that nature is continuous. So if I have two atoms and I do small perturbation, I don't expect the wave function to be completely different, but it should change in a continuous fashion according to my perturbations on the structure. And the idea now is we exploit this correlation and this continuous change, and by capturing the change in the geometry with a GNN. So we apply GNN on the structure, and then we learn what changes in the structure. Like if we do some changes, we notice, okay, this is distinct structure, this is distinct structure, and we can interpolate between these two. And if we can encode the structure in our GNN, then we can return parameters for the wave function model again. So now the idea is, instead of the parameters being optimized for each structure from scratch, we have some shared parameters, and then we adapt other parameters such that they adapt to the new problem which you're given. This comes with additional benefits that we can integrate physical symmetries. For instance, like if you have a molecule in vacuum, if you rotate the molecule or you translate it in space or you reflect it, its energy doesn't change because like, there's no reference point. This doesn't matter. So the molecule itself is invariant against, like the energy is invariant against this, and we want to encode this in our new model as well. Unfortunately, we're running into a small issue here, where I just said like the energy is invariant to translation, rotation, and reflection. The wave function is not. A simple counterexample you can think of is like if you have the hydrogen atom, which is like you have one point in space in vacuum, and you have one electron floating around that somehow. And if you then look at the solutions to the Schrödinger equation, which are the spherical harmonics in this case, if you look at the ground state, which is here at the very top, that's spherically symmetric. So it doesn't matter if I rotate the whole thing, the wave function will always be the same. It doesn't have these symmetries. But if you look at all the excited states, which are all the below, these have different energy values. So the different eigenfunctions of the Hamiltonian. But they're all valid wave functions. They need some directionality in space, right? They are not invariant to rotation. If I rotate, for example, this wave function here, I get a different energy value from my electron. I cannot hear you. I think you're muted.
Thank you. Isn't this sort of a bad example now for our case to say that we, so first of all, what you want to say is that we don't want to be invariant, we want to be equivariant in this case, or the output of your network should be equivariant. But isn't this now not a little bit of a bad example, because we actually always want to find the wave function of the lowest energy state, where here you have the sphere and you are actually invariant?
You're right, like the lowest energy state is invariant, but our goal is in general being able to model arbitrary wave functions, and arbitrary wave functions do not have these. Like, because the others are all valid eigenstates, there exist other molecules. Like, the problem with plotting higher, like other energy surfaces in hydrogen, because there are many body functions, it's not really plottable anymore. So this is the easiest example you can essentially plot.
But with your variational Monte-Carlo approach, are you actually able to get all of the eigenstates, or will you only find the lowest energy one?
We will only find the lowest energy one. There are works which extends us to finding other energy states, and essentially works by orthogonalization. So you say you have, your ground state, so you just try to find a function which is orthogonal to your ground state, and then you will find the second lowest eigenvalue.
Okay, but now if we're going back to imagining our electrons swirling around the atom or the proton for our hydrogen, and you're now saying what we see over here are like the regions of high probability of the electron to appear, right? That's what we're drawing here.
What's plotted here is the surface of the spherical harmonics at a value of 1, because they're defined on the distance of 1.
So it is like the area where we appear with a high, or inside of these regions we appear with a higher probability than outside.
Yes.
And now for the first one, the lowest energy one, absolutely makes sense. And there are infinitely many of those, right? There are not just 4 rows, there will be infinitely more rows.
Yes.
And, but now let's just go with the second one. You're telling me that it's sort of an equilibrium state. Is that correct?
No, it's an excited state. It's an excited state. Like all the non-ground, like the lowest state is called the ground state, and all the others are called excited states because they have higher energy values. So they naturally they don't want to stay in that state, but get rid of the energy somehow.
Okay, but so if I pump a little bit of energy into my system, and there's now more energy than there should be, then if it's the right amount, then we will have these probability distributions and no longer the top probability distribution.
Yes, yes. If you think about it that way, yes.
Wow. Okay. And so, and then the electron swirls around. But I mean, there's no.
They don't swirl. They're not particles. Like this is again the wave
but,
particle
I mean,
duality.
Yeah, we can. It's the same, right? The electron swirling around. What we mean if we say that is that the probability distribution is such and such. Yeah. Then so, but will there just be a randomly chosen direction or a randomly chosen coordinate frame in which these orbitals then establish themselves?
Yes, it's just arbitrary in a sense.
Amazing.
Like in vacuum it's arbitrary, but things in nature are not in vacuum, so then it's not arbitrary anymore. But in vacuum it's arbitrary.
And this is like some real quantum randomness, right? Some absolute randomness.
That I don't know exactly the answer to.
It's not just that the direction can be random, but also like there can be easily jumps between these different. So like it's not like you'll have you won't necessarily have like something in that state in permanence, but like you could have something in that state and then it jumps to that other state here, then jumps back to the other state, and so on. And even like well, when you look at only one molecule, it's going to stay at the same energy. But if you look at the system of many molecules or many different atoms, like in a gas of hydrogen, for example, the different molecules will exchange energy between each other, and it's not true that you will like if you are at higher energy, you will never see this ground state here, because in fact some atoms will have lower energy than others, and so on. So in general, you always find many states, and the atoms jump between different states. It's not it's not necessarily fixed, unless you have some coupled states, but this is a bit more complex to discuss. So one question I'd like to ask here is like you said that in your work you focus on this energy here, but during the optimization, will you not pass through all these other functions before reaching that, or not really? You try to reach that point directly?
Well, your initialization will be because your initialization is somewhat random. You will state at some linear combination of all of these states, because again, these are like eigenfunctions. You will start with some linear combination, and eventually you will just evolve directly to the ground state. The problem is with bad initialization. Oh wait, why is my screen turning blank? With bad initialization, you can, if you start orthogonal to your ground state, you will not end up in your ground state because there's just no way to get there.
Yeah.
Similar to power iteration, if you start orthogonal to the largest eigenvector, then you also will never get the largest eigenvector.
Okay, so you need an initialization that has a bit of every wave function, because you cannot escape orthogonality. They are local minima.
Yes.
During the optimization. Okay, great. And are you working or are you tackling the wave function at 0 Kelvin, or
yes, these are also U Kelvin. No, these are also U Kelvin. Variational Monte-Carlo is not super trivial to extend to room temperature, for example. It just works at 0 Kelvin.
Okay, great. Yeah, so in that case, you will end up with the lowest energy state, I suppose. Okay, thanks.
Okay, this is amazing, Nicholas. Thank you so much for teaching me.
You're welcome.
Okay, cool. But summary, we have these our wave function, which now with our variational Monte-Carlo, we're going through all of these levels, and now we finally want to end up at the top level. If we look at the second level, for example, there we first choose an arbitrary or nature chooses an arbitrary rotation rotation in which or an arbitrary axis, and according to that we have these orbitals. And if we now rotate our coordinate system, then these orbitals will rotate with them as well. So we want the thingy that we want our wave function, right? Because this will be drawing our orbitals later on, our wave function. We want that to be equivariant and not just invariant. Because even though here in the the lowest energy state, the sphere is actually round and invariant to rotations, in maybe bigger molecules, this will no longer be a sphere, and it would be, we will need the rotation and translation and reflection. Okay, well, we don't need the translation invariance, but we need rotation and reflection equivariance, and we don't want to be invariant.
Right. So the function must be equivariant, which is not to confuse with like equivariant outputs, because there also exists the whole literature on equivariant neural networks, which predict equivariant properties. So the wave function itself, because it's just a scalar output, is obviously in invariant measure, but the function itself must be equivariant, meaning that the function rotates in space, not the output. So this is just to make this clear, because there are also these equivariant networks which predict equivariant vectors, but this is not what we're doing here.
Yeah.
So yes, so how do we resolve the problem that we need some coordinate system, and the solution is we just define one. And as Hannes correctly pointed out, we want to have been equivariant, meaning that if we rotate the molecule, our coordinate frame rotates accordingly. And yeah, when we simply implement this, but you see, for example, what we do here is we need to take all the nuclei and then compute the principal component, do the PCA, principal component analysis, and takes like the free principal component as the axes. And then we do several tricks to resolve sign ambiguity and stuff like that, because eigenvectors are generally not directional. So we have to resolve this. We do some tricks there. And then we end up with some coordinate frame in which we can work.
So you take the, okay, no, you do PCA. I get it.
Yeah, in a more physical interpretation, this would be like the moment of inertia, like the of your point cloud, of your mass in a sense. But in a more computer science point of view, this is like, we can just call it the principal components of our point cloud. Yes, and then we just use these as coordinate frame, and then we have the desired property. And if we as Dominic correctly pointed out, for example, if we had an excited state and these randomly flip, it doesn't matter, because the wave function is also just randomly flipping, and it's completely okay. We just need to be able to distinguish it.
Are you saying that the first principal component, if we place it at the center of mass, that is the moment? I mean, no. Can you say the whole moment of inertia thing? Like,
well, like the moment of inertia, like the axis along the highest inertia, like the same as highest variance in like data terms, like if you see it as data. So this is just a physical interpretation. Like it, I'm not a physicist or mechanical engineer, so I would have to think like it means that you are less, like it takes the most energy to move.
Okay, but
axes,
I mean, the moment of inertia is defined with respect to an axis, right?
Like the axis, like the PCA is the axis then of the moment of inertia, right? If you center everything at 0.
Okay. No. Anyway, let's that.
You can find the three principal axes around the inertia, like where if you take the principal axis, it's where the inertia is the highest, and the other is the axis with which the inertia is the highest, and the highest eigenvalues where the inertia is the lowest, or maybe I inverted highest and lowest. But anyways, yeah, you can find these three axes that give you the highest inertia and lowest inertia with principal component analysis.
Okay, here, but those I have to put at the center of mass, right?
Yeah. I always put the quantum system in the center of mass. Everything is centered at 0. You can just arbitrarily subtract the mean of everything.
Well, inertia is by definition computed as the center of mass. Or like you can compute
no.
Yeah.
That's not
that's
true.
true. That's not true. Yeah, you can rotate something according to another axis, but yeah, in terms of like when you deal with molecules, especially in empty space, there's only like
Yes.
around itself that it can turn. One thing I want to say here is like yeah, the idea here is that you want to find like there are infinitely many axes that you can find, and you need to define a set of axes such that the network can learn. And for those in the audience that are familiar with the directional graph network paper, it's exactly the same trick that was used also using the principal component to find a set of direction that makes the most sense and that the network can generalize. So here it's the same trick, but done in 3D space instead. So finding a set of axes such that, like, in general, the axis will change very little if you add or remove an atom, unless you're in a highly symmetric molecule, where then it can shift a lot. But if you have some very long molecule, then adding an atom or removing an atom will rarely change the principal axis in general.
So you just calculate those the PCA, and then you normalize your molecule according to that, the rotation of it, and this means that you will always have the same rotation of the molecule no matter how you rotated it initially.
Exactly. Yeah,
okay.
that's the general idea here, that we're working in a normalized coordinate system that we can generalize a bit better. Yeah, so next we can put these things together. So we had, like, as we discussed in the beginning, we had this idea with the GNN, which takes and then our wave function model. And the general idea is that we have our again our GNN, where we take the geometry. In this case, we only have 2 atoms, so these big blobs here, these are atoms. And so our GNN, our meta GNN, we just call it, like, analogy to meta learning, takes the nuclear position as input, and then depending on geometry, we output some parameters for a wave function model, which we can use like FermiNet or PortNet or whatever. We just did FermiNet from David Pfau, which then in turn takes the electron position as an input and gives you the amplitude of the wave function. So, and the beauty about this whole procedure here is that everything is end-to-end differentiable, and because we can take different nuclear positions as an input, we can also train a single model for a whole energy surface. By just having a batch of different geometries, feeding them in like you would normally do, and then you compute the gradients for everything and just backprop through the whole network. So you would obtain gradients for your wave function, which you then backprop through the parameters to your meta GNN, and then you can train everything in one way, which is neat because you don't have to deal with lots of optimization problems. Yes, and if you then now get some experimental results, here we, for example, show that, like, we can integrate this symmetry successfully on a system where we have like 4 hydrogen atoms in a rectangle, and we change the angle between them. And so every angle, like before 90 degrees, is symmetric to every angle not after 90 degrees, because we're just like moving the rectangle. What we can also see that, like, our potential energy service network, like, is with FermiNet, which is our baseline model, and very much exactly at like full configuration interaction, which, if you remember from the very beginning, is this factorially scaling method, the holy grail, which is completely infeasible for larger systems, but for this, like such small systems, you can actually compute it. They're identical, and you cannot distinguish them anymore. So these are super accurate numbers, and we can also see that, like, we only train on the first angle, like geometries from the first part, and then we can generalize to the other part because we integrated these symmetries into our network. And then we have some curious, like some comparisons on more difficult molecules. Here we have a hydrogen chain, and there you have the nitrogen molecule. And the general takeaway is here that we train always a single model for all of these, like, for example, on the right plot, for all of these blue data points, which are potential energy surface networks, we only trained a single model. Well, for the orange one, you had to do like 32, I think, data points there are, 32 separate network evaluations, or train 32 different models. So we can show you that by training on all of these configurations simultaneously, we don't actually lose accuracy. So here we are pretty much even, and here we are like even a little bit below. Yeah.
So no, Dom, you go ahead.
So here, like the graphs are identical, no matter the distance here. So are you using a graph neural network or like more a 3D GNN, like a 3D network like that takes like something like a SphereNet or like something like GIN, for example?
No, we used to like the meta GNN, like you mean for a wave function model or for the meta GNN?
Yeah, for the meta GNN.
That's actually, I think, the simplest GNN you could implement. Like it has just some MLP as update function, some MLP as message construction function, and only works the distances. So it's like more like SCHNet, but even simpler than that.
Okay.
But like it does not only work with distances, right? It also takes the actual coordinates as input that you have normalized.
Right.
To be, yeah.
And in addition to the normal just invariant properties, we also use the coordinate frame for our meta GNN. So we use the raw XYZ coordinates also as input to the network because they are also transformed into this normalized space where we work in.
Okay.
And we do this to get like different, like for example, like in this case with nitrogen, if we wouldn't do this, both of these, all parameters which we associate with one atom must also be identical to the other one, which we found is suboptimal and does not yield ground state energies. So we left this requirement by including the XYZ coordinates in the meta GNN.
Okay, makes sense. And you said here that you trained a single network for all n distances, but did you also train the same network for the NN than the hydrogen chain? Or like, is this two different networks that you...
These are two different networks. These are two different networks. It doesn't generalize across systems because there are certain restrictions, certain parameters, numbers are dependent on the number of electrons, so it doesn't generalize across systems. This is definitely an interesting future work direction, but this one only focuses on different geometries of the same system. Okay.
And have you considered also like more complex 3D geometries than just the distances? I guess maybe next slides.
Yes, we have like as systems or as models, you mean?
Like for example, the chain of hydrogen on the left, like by changing the distances, it's kind of trivial that it remains a chain, but by changing the angles, you can have so much more diversity in the output.
Yeah, that's generally a problem that like you're definitely right, but larger systems tend to have many electrons. Like as you can see, like this has 10 electrons, this has 14 electrons. These are relatively small systems. Any system with high degrees of freedoms tend to have many electrons, and many electrons usually involve, it makes the whole thing more difficult. But actually, yes, we have looked into that. This is not in these presentation slides here. This is actually on my current Europe submission. We could look at things in preprint paper where we want to investigate how does it behave, like can we generalize to systems where you like twist angles and stuff like that, which we unfortunately didn't do here because like these systems are rather small. But in future work we looked into that. The last experiment I have here for you is, for example, on like this is also a larger system, but we also again here look only at two states. For example, here on the left we see the ground state of that system. On the right we see on the curve struct, the ground state. On the right you also see the ground state, but just rotated by 90 degrees. And then we have the transition in the middle where it's symmetric. And then we want to find like how much energy delta is between these two. And we can see that our potential energy surface network, which is also very accurately here in blue in the bottom, which is the transition barrier, like the delta between these two, quickly converges to the same values as the other networks, in line with experimental data and highly accurate reference calculations. An interesting finding which we found here is that if you don't use the meta GNN, but just train one network on both states directly without this reparameterization, it performs significantly worse. So this meta GNN actually helps in modeling like the states with high accuracy, and we can observe the same behavior in the nitrogen molecule, but this isn't plotted here. And then to the most important part of our experimental evaluations is like, what do we save here? And here we have like our 4 system or 5 systems we just introduced you. Well, okay, one I didn't introduce you to, but as the systems I introduced you to, and the compute time it took. And since our accuracy is mostly very similar to FermiNet, we should compare to the FermiNet row here. And we can see that our potential energy surface network offers huge savings in terms of compute time, just because we can solve many at once and don't have to do like 40 evaluations, but we just do one training and then can get arbitrary energy values for each of the geometries. Even though you might see the 90 hours still a lot, but way less than 4,200 hours.
How does this compare to like traditional methods?
That's a good comparison. I actually have not run these traditional comparisons. Like these are, it's always difficult because you want to compare similar accuracy, right? I can also always make everything fast if I make it less accurate. For instance, the hard before calculations are running in less than a second, but they're way less accurate than these ones. DFT is also super fast for these kind of molecules. So this is also nothing to worry about. But if you run coupled cluster calculations with large basis set extrapolation, like this is again very, very like these quantum chemistry people, they usually pick basis functions and then define the wave functions linear combinations between these. And usually what you do then is you extrapolate, like you do that from different numbers of basis functions, and then you extrapolate to infinitely many basis functions. And if you do, for example, coupled cluster calculations with this extrapolation to infinitely many basis functions, that takes quite some time, but unfortunately I don't have a number for you. I just know that it's not in the range of minutes or something like that.
Okay, but for similar quality to what you have, like how much would a standard system take to compute that?
We have not evaluated like again the classical baselines. I think, for example, on nitrogen, I haven't plotted any comparisons to classical methods here. But for example, this coupled cluster, which I just talked about, they are way less accurate than our method here. So even if you extrapolate to infinitely many basis functions, it's way less accurate. Okay. The other factorial scaling methods, which are then with some finite basis set applied, and then you can get reference values. But I don't know the compute time of these.
Okay, great. Yeah, makes sense.
And then we already end the last slide of my presentation. So to quickly summarize, like I presented our potential energy surface network, where we explicitly exploit the correlation between wave functions and their geometries, such that we can efficiently reparameterize our network and use the symmetries of our energies to reduce the dynamic space. And in our experimental evaluations, if you just saw, this results in no loss of accuracy, but significant time savings, bringing us closer to actually making these methods practically applicable to any reasonable size system. And yes, so this would be my presentation slides here. If you have any questions, I'm very happy to answer.
There are, of course, many questions. But now, first of all, thank you. This is lovely. This has already been such a lovely discussion, or maybe not so much of a discussion, but you teaching us a lot, at least me. Yeah, if there are any questions from others, always go ahead and raise your hand. But from my side now, can we go back to your slide where you also like 8, I think, where you also had your drawing with the red stuff, your red drawings? No, okay, a little further back.
My red drawings, okay, this one.
Yeah, nice, exactly. Yeah, cool. We have this energy formula. Right, and you already wanted to write out the integral. Let me maybe go ahead and take my own pen here. Yeah, and right, you have this integral of the psi squared, and then we have this thing here, and this thing here is psi inverse h psi. So is this not just the same then as the integral of this thingy here?
Yes, yeah, definitely. Yes, this is correct observation. And actually, you get from the lower equation which you wrote to the upper one, because you want to expand it by multiplying with psi to the -1 times psi to get to the psi square, because that you can interpret as a probability distribution. And I forgot the name of the trick. Essentially, then you can evaluate the integral by sampling the probability distribution. Like if you have an integral where you have probability distribution times some function, you can approximate the integral rather than doing like a grid sampling and evaluating every data point. You can sample the probability distribution and then evaluate it for that, and then you get the Monte-Carlo estimate, which does not have the curse of dimensionality, because then our error scales 1 over square root of n, where n is the number of samples, rather than the number of grid points in an exponentially growing space. So reformulate importance sampling. Importance sampling is the name for that. So you can do importance sampling by reformulating it, and this gives you better error estimates than doing grid sampling.
So you're not just doing this.
Yes, we're doing a Monte-Carlo estimate of the integral.
Okay, I thought you're doing some important sampling tricks to get a better variance, I think, or.
Yeah, essentially, this is a better solution than doing grid sampling. Like if you want to integrate a function, you could like discretize it on the grid and then evaluate it on the grid. But if your function gets to higher dimensional spaces, the number of grid points you need scales exponentially. So by doing importance sampling and sampling the probability distribution, you get a scaling which is way more favorable, independent of your space, by just being 1 over square root of n.
Yeah. Okay. Thank you. This is all very, very nicely explained by you. That's amazing. We have what other questions that come to my mind? I don't know. You've already answered so much. Can we maybe go back to the slides where you have the spherical harmonics? So we also at one point, or Dom said that we're sort of going through all of these. Maybe in the beginning we start with a wave function that is at the energy excited states 1 million, and then we're going through all of these. Is that something we can say that we're doing in our variational Monte-Carlo approach, or is that very like the wave function that we start with probably does not correspond to any
exactly. As I said, because they're infinitely many, they're a complete set of all functions you could define. So because you have this infinite dimensional function space, and you have these infinite many functions which are built a basis for all functions you could define. And we will start, obviously, like if you draw a random vector, it will be a linear combination of some complete basis set. And this is the same here. We start with a randomly initialized new network, which will be some linear combination of some of these states, like preferably all of them. Because if you draw random vectors, they're very unlikely to be have zero contribution to any of your bases. So it will be non-orthogonal to all of them, and then you just optimize it to project essentially to the ground state.
But yeah, okay, nice. Simon, you had a question, or you raised your hand. Do you want to comment?
No, it's fine. Just wanted to clarify that when you're doing your Hamiltonian expectation with psi h psi, your first psi is actually transpose conjugate. So the -1 also means that you flip the phase. You have to keep in mind that those wave functions are actually complex, so they have an imaginary component.
Actually, for the time independent Schrödinger equation, all of them are real, so we don't have the conjugate.
You choose them to be real, but you don't have to.
You're right. You don't have to. You don't have to. Right. You don't have to. But the we know that the eigenstates are real. So at least the lowest one, the ground state is real. So we don't need to.
You choose the phase so that they're real. Actually, right?
That might be. I'm not a physicist.
Okay. I am. So this is
okay. You will know. You know. Yes.
But it's okay. It's a valid choice. It's fun.
Thanks for changing that.
Thank you, Simon. This is nice. But okay, also to you, to me, you're both physicists. Okay, no, let me not say that because that would be maybe unfair for Simon. But to both of you, now I know spherical harmonics only from my tensor field networks and where I use them there, and to me they don't necessarily need to have anything to do with hydrogen solutions and so on. And now for me the spherical harmonics are something that I can give a vector, and then it gives me the irreducible representations that transform, or like of dimension 0, of dimension 1, or of dimension 3 or 5, that transform equivalently under rotations. And now these are just matrices, right? How do these matrices correspond to, yeah, how do these functions here correspond to these drawings and to the wave function and probabilities of a state being somewhere? What is the connection between the wave functions and the spherical harmonics?
Okay, so maybe I can answer that if you don't mind. So your wave function, basically, for the hydrogen atom, you can express it as a product of an angular function and a radial function. And the solution for your angular function, because your Hamiltonian will be invariant to rotation, the solution will be the spherical harmonics. Okay, and that's where those things comes out. And it turns out that your lowest energy, which also called the 1s.
I couldn't follow. So we can express our wave function instead of having a single coordinate. We instead of having an x3 coordinate as input to a wave function that gives us then a number, we now have a radius and we have 2 angles.
Yes, so spherical coordinates. So you have the radius, you have the polar angle and the angular angle. And Dominic just wrote exactly that. So when you factorize this, you can actually show that the radial function is an exponential function times some polynomial of r, which is fine. But that's characterized by one integer, which we call n. So 1, 2, 3, 4, 5. And then you have the y function, which is going to be the spherical harmonics parameterized by 2 numbers, Lm, and that's your angular momentum. And basically, it turns out that there are some constraints when you solve this in the Hamiltonian, and the solution, the lowest energy solution, is going to be just a simple exponential decay for r and a constant value for y. And that's your first, the sphere. So that's the 1s orbital. And then your second one is lowest energy is going to be 2s. And it's going to actually have the same solution. And there's another solution, which is the 2p orbitals. And that's the second line that you see here.
Okay. But
and then you have the 3s, 3p, and 3d. And that's the first, that's the second highest, third lowest, sorry, energy, and that's the sphere, the second line of and your
Lovely. Okay, and the r for all of my energy levels does the R stay the same, like the R of R?
No, it basically becomes more and more, if I remember correctly, just decays faster the higher energy.
Okay.
Basically, when you have low energy, you can imagine that the electron is infinitely far from the nucleus for the lowest energy configuration, for example.
Okay.
Yeah.
So in this case, the spherical harmonics take two scalars input. Okay. No, thank you all very much. This has been very nice, but I'll read about this some more at some other point. I also don't want to bore Nicholas here with while Simon explains interesting things. Yeah, no more questions from my side. So I think we can all just say a last thank you, a very big one, for the presentation and for the great discussion. Very lively. Yeah.
Thanks a lot, Nicholas, for the great presentation and discussion. I have one more question. Like, if you have time, can you go back to where you discussed what is the what's called like the wave function network? Like, how is this defined? I just
You mean here?
Yeah. So in that slide, I didn't understand really like what's the architecture and how things are done. So this one is used in combination to your meta GNN, right?
Yes, exactly.
Yeah. Okay.
So this is not the whole network. This is a very heavy simplification for the network. But I can just explain, for example, how the Fermi net looks like. It's not a lot more. So you have you first constructing two kinds of features. You have single electron features and pairwise electron features. The pairwise electron features are very straightforward. You take two electrons and then just the delta between these two. So x delta, y delta, z delta plus the distance. So it's a four-dimensional vector for each of the n squared combinations. So this is your pairwise features. And then you have your single features, single electron features, which are just a concatenation across all atoms. So you do the same construction, you compute the distances between each electron and each atom, and then you concatenate all of these distances again. And these are the input features. So they're very basic in a sense. They're not like advanced process or whatever compared to like other networks. And then they update them over a few interaction layers. And an interaction layer, for example, looks like for the pairwise stream is very straightforward. It's just like each item is updated independently. You can imagine playing 1-by-1 convolution over this like n squared grid. And then you just do that. And for the single streams, single electron features, they are updated by you take your single electron feature, you take the global mean of all spin up. I completely neglected the spin states. You usually have spin up, spin down states, which we dropped here for simplicity. But generally, you complete global means over your electrons, and then a mean, and then also means across the pairwise interactions this electron's involved in. And then you just concatenate this to a long vector, feed it for a linear layer, apply a nonlinear function, and do this multiple times. And this is a very simple thing. You can imagine it being like a fully connected GNN. Yeah.
So in some sense,
and then in the end, you get your electron embedding. So each node gets an embedding, and then you multiply it with these envelope function, which we plotted here below, where we compute the distance from that electron to each nucleus, have this exponential decay, sum over them, and multiply it with the electron embeddings, and then we just concatenate them to get the matrix. And here's also the part where it doesn't generalize across different molecules, because we can only compute the determinant of square matrices. We need the network to output vectors of the dimensionality of the number of electrons. So this is why this is now So we must have some matrix there, which is like this fixed size of being like whatever hidden dimension before times n. And if now this n would be something different for a different molecule, it doesn't straightforwardly apply there. And then, yeah, again, concatenate these and takes a determinant.
Okay. So n here is the number of electrons at a given atom, or yeah. So basically,
Yes.
You learn a wave function at one atom. Then with the 3D network, you interact with them, and then you go back at single atom, and then at interaction, and so on.
Oh no! We do all we do all the. It's not per atom. It's like n is the number of electrons in the whole system for all atoms. Because this anti-symmetry here must hold for all electrons, and we don't assign electrons to atoms because physically they're not assigned to atoms.
Okay, I see. Okay, thanks. That makes a lot of sense. Thanks.
Samar also has a question.
Hey, just a quick question. So is the determinant here meant to be something similar to a Slater determinant?
Yes, exactly. It's the same principle as the Slater determinant. The Slater determinant, you have usually like these single electron functions. We have like many electron functions as orbitals, but then it's the same thing, yes. Also, practically, we don't use a single determinant, but we use linear combinations of them. But these are, again, just technical details. Alexander asked, were any tricks are used to not compute the determinant explicitly? No, we have to, like, I know that in quantum Monte-Carlo, if you use basis sets instead of these new networks and use linear combinations of these, you can do tricks to avoid computing the determinant, because normally computing the determinant is n to the 3. And if you use these tricks, you can do it in n to the 2 or in n squared. But no, we don't use anything here because with the new network, it's really hard to know what's going on there.
And lovely discussion. So many of my questions answered here by Nicholas. I hope some of yours as well. And if you want to ask your own questions, well, you have to join yourself. Just raise your hand and then go ahead. So all the information to join is down in the description, and maybe see you around.